Hi, I would like to do an example over least squares regression, and I want to cover some things from 4.1 and 4.2. This problem actually came from the textbook, and it's problem number 20 in section 4.2. But I added some stuff to it, so that way we covered stuff in 4.1 and 4.2, and kind of did like a holistic view of a least squares regression. This example, it's the American black bear is one of the 8 bear species in the world. It is the smallest North American bear and the most common bear species on the planet. So in 1969, Dr. Michael Pelton of the University of Tennessee initiated a long-term study of the population in the Great Smoky Mountains National Park. So one aspect of the study was to develop a model that could be used to predict a bear's weight, since it's not practical to weigh the bears in the field, right? So, it's much easier to carry, like some type of measuring device over something to pick up the bear and put it on some kind of scale and weigh the bear, right? That's not very practical. So we often like to use models, for things that aren't practical or maybe unsafe, etc. So one variable thought to be related to the weight is the length of the bear, right? So we're thinking maybe if we know the length of the bear, we can predict its weight. So the data below represents the length of 12 American black bears. This data is saved in an Excel file on Canvas, named 4_2_20.csv, right? So I have that listed here, but also in an Excel file on Canvas. And this is the source from the data, right? So typically, if we're doing research, they probably had more than 12 bears, but that's what we're given, right? Maybe they only had 12, but I would think they maybe had more than that, but who knows? I thought this data was interesting, because personally I've been to the Great Smoky Mountains, so I thought I would just share a picture in case you've never been. But this is a picture I took while I was at Pigeon, Tennessee, which is in the Great Smoky Mountains. So I went there with my family, and my son had a week-long baseball tournament there at the Cal Ripken Junior Experience. So you can see here's a picture of the mountains, and there's a rainbow here in the middle. So I thought that was a really nice picture. And then we saw some black bear while we were there, but not this close. This picture was from one of our teammates' parents. They took a picture. They had a bear right by their cabin, so they were in their car and took this picture. So they saw one pretty up close. We saw one way in the distance. But yeah. So there's a black bear in the Smoky Mountains, in case you've never seen, right? So these are what the tasks that we want to do. So the first thing when you're looking at some data, remember you want to start with looking at a picture first, right? So I have here just a look at a scatter diagram of the data in StatCrunch. So if you go to Canvas and go to My Lab and Mastering, you can click Open My Lab and Mastering, and then click on StatCrunch, and then you can click on data sets from your textbook, and we want chapter 4, and it was 4_220. So this is just one way to access it and have the data already pulled in StatCrunch, or you could copy and paste from the Excel document that I posted on Canvas, right? So we want to look at a picture, so we'll go to Graph, and then go to Scatter Plot. So the X variable that we were using is total length, and the Y variable is weight, right? And it's pretty typical that when you're doing research, the first variable you list is the X, the second variable you list is the Y variable, but that's not necessarily true. But notice I labeled here X and Y, right, to make it clear. And then later on, I tell you to find the least squares regression line using total length as the explanatory variable, which is X, and the weight as the response variable, which is Y, right? So that's how we know that, right? Because remember, it's not always clear maybe what would be the best explanatory and response variable. It depends on the research question, right? So what we're trying to do is take the length of the bear to predict the weight, right? because that's what we want to do. So I can hit compute, and here's my scatter plot. Right, so I'm gonna copy this image and paste that in to my file here. Right, so you can see by looking at this scatter diagram, it looks to have a linear trend, right? So if I just kind of eyeball this, it looks like maybe it has this linear fashion, something like this, right? So it looks like it could work, right? It looks like it could be linear. So then remember, we have a test to see if something's linear as well. What we have to do is calculate the linear coefficient first, R. Right, so if I go back into my StatCrunch, I can go to data, and I can go to, we go to stat and then summary stats, and then go to correlation, and we pick our two variables and hit compute. And then, so there's my R value, right? So I'm going to insert an equation into Word, just type this, or you could write this down. So R is approximately 0.7039, right? So technically, mathematically, we would want to use the approximately equal to symbol like this, but it's often the case that we round in in statistics, and we just say R equals, and then just round a specific number of decimal places. Right. So then now what we want to do is to use the critical value from Table 2 in Appendix A to determine if a linear relation exists between the two variables, right? So I looked at a picture, a linear relationship seems feasible, right? We've calculated the R value, so that seems to look promising, and now we'll test, right? So remember, what we need to know is the sample size, right? So n equals 12 here, right? That's my sample size. And I know that because there were 12 bears, right? And if it didn't state that, right, we could count the number of rows that we have, and there's 12 rows. So if I look down at this diagram, right, so this is my table. I put it in here. So we look for 12. That's the critical value that I'm looking for, 0.576. Right, so let me deselect this highlighter there. Right, so the critical value equals, I forgot what it was now. It was 0.576. 0.576. Right? So, if I insert an equation here, we want absolute value symbols, right? So the absolute value of R, which is equal to the absolute value of 0.7039 equals 0.7039, which is greater than the critical value, which equals 0.576. Right? So, therefore, a linear relation exists. Right? Since our correlation coefficient, the absolute value of that, is bigger than the critical value, right? And in fact, we could comment that, more specifically, a positive linear relation exists. Right, and we know that because the R value is positive, right? And we can also tell that by looking at the data, right? So the longer the bear, the more weight, the more that the bear tends to weigh, right? Which seems realistic. right? So then we want to make a statement speaking about the shape, strength, and association of the data from what we know, right? So we could say the total length and weight variables from the 12 black bears appear to be or we could say are moderately or let me try to make this sound better. The total length and weight variables from the 12 black bears have a moderately strong positive linear relationship. Right? Or instead of relationship, we could say correlation. Right? So why I'm saying moderately strong, so if you remember from the notes, we typically say, moderately positive if R is around 0.4 and strong if R is around 0.9. So we're kind of in the middle, right? So this seems to be, moderately strong. So we're like in the middle between moderate and strong. We know it's positive because R is positive and it looks to have a linear correlation, right? And we can tell that from the kind of overall shape from the data and then also from this test in part C, right? So then the next thing we're asked to do is to find the least squares regression line, treating total length as the explanatory variable and weight as the response variable, right? So I'm going to go ahead and start my equation. So remember, for the y variable, it's typical that we need to use that hat symbol, which is here, and it's typical that we, in statistics we state kind of like use a word instead of y and x, so that way it makes more sense, right? So we could say the weight, so the weight hat equals, and then we're going to have some number, times the length of the bear, and then plus some y-intercept, right? So we need to figure out what those two values are. So using StatCrunch, we can go to let's see, stat, regression, and then simple linear, right? And that'll pull up this where I can input the x variable and the y variable, and I can hit compute. And it gives me this nice table for those values, right? So what we're looking at is this equation, right? Or we could find the intercept and the slope from this table right here, right? Either place. So I can plug those in now. So the slope was 1.694 roughly, so I'll round to 3 decimal places. Or we can do, let's do 4, 1.6942, and then the y-intercept was negative, so I'll do minus 142.4709, right? If I want 4 decimal places. Right, so that's my linear equation. Right, so now we're asked to interpret the slope and y-intercept if appropriate. So we could interpret the slope. So the x variable, the change in x, is 1 centimeter, right? So in other words, that slope value is positive. So we're going to increase 1.69 kilograms. That's what our weight's measured in, and for every one additional centimeter in length, right? So to put that in words, we could say for each centimeter increase in length, the weight of the bear will increase by 1.6942 kilograms on average, right? So remember, we say this on average part because where those y hat values are averages, right, for those particular x values. And then if you think about for the y-intercept, right, that y-intercept value, this negative 142 number, that's going to represent the prediction of a weight of a bear if they are 0 centimeters in length, right? So a couple of things wrong here. One, it doesn't make sense for us to have negative weight, right? Also, it doesn't make sense for us to have a bear that measures 0 centimeters in length, right? You don't have a bear then, right? That's really silly to think about. So it's not appropriate. It doesn't make sense to interpret that y-intercept here, right? So it is not appropriate to interpret the y-intercept because a length of 0 centimeters, oops, that's a typo, for a bear does not make sense, right? And we also discussed, it also doesn't make sense to have a bear that weighs negative weight. All right, that's just another comment. Right. So then part G, it says suppose a 149 centimeter bear is captured in the field. Use the least squares regression line to predict the weight of the bear. Right. So we could take this equation, right? And what I'm doing is I'm filling in instead of length, I'm filling in 149 centimeters, right? So we have 149.0, but that 0 probably just indicates that you rounded. So we don't have, it doesn't make a difference in our calculation, right? So I could just write 149, but it's common to write like 0.0 if you've rounded to that number just to indicate the rounding, right? So like if you're trying to have everything round to the nearest 10th decimal spot. So we could use our calculator to come up with this number, right? So I'm just plugging this into my calculator. So I have 1.6942 times 149 minus 142.4709. I'm getting 109.9649 as my answer, right? So if we round that to the nearest kilogram, that's going to be, approximately 110 kilograms. Right, so this was also in kilograms. Right, so in other words, our model predicts that a bear that is 149 centimeters in length will weigh 110 kilograms. Right? Or if we wanted to be really specific, right, we could say that our model predicts that the average weight of a bear that is 149 centimeters in length is 110 kilograms, right? Because that hat value, remember, that's the average value, right? For all the variables that would have this x value, that's going to be the average weight. Right. So then now the next part is to calculate the residual, and we're asked, is this bear's weight above or below average for a bear of this length? Right, so remember the equation for a residual. We use E to denote the residual, right? You can think of E like error, right? The residual is equal to E equals Y minus Y hat, the observed minus the predicted, right? So just gonna fill in this hat symbol, right? So that's, the equation typically, right? But in our case, we're not using the y variable. Our context is the y variable is weight, right? So we're going to take the weight minus the weight hat. So if I look at my data set for 149, I had a bear that had a length of 149 centimeters and weighed 85 kilograms, right? So I can, so that's going to be what my weight is. So 85 kilograms minus, and then my y hat value would be what my model predicted, 110 kilograms. So 85 minus 110 is negative 25 kilograms. Right, so that's the error. Right? So it says, is the bear's weight above or below average for a bear of this length? Right? So the average weight would be the 110 kilograms, and my weight of the bear I had was 85 kilograms. Right? So the bear's weight is below average for a bear of this length. Right? We're below average because 85 kilograms is smaller than 110 kilograms. Right? Right. So what I would like to do now is look at part H, but look at it from a more visual perspective. Right? I guess parts G and H in a sense. Right? So if I go back to StatCrunch, and I'm going to StatCrunch and results hidden, and the simple linear regression is what we were looking at, right? So this is where we got the least squares regression line equation. If I click on this down arrow down here, it gives me a nice scatter plot, and it plots that red line on the scatter plot, the fitted line, right? So I'm going to copy this image, and just put this in our notes here. Right. So then, if you look at the data, what I'm going to try to identify is that value that's 85. Or wait, no, not 85, but 149 centimeters. Right. So the 149 centimeters is 149 85. Right, so this this data point here should be the data point that we're after. Right, so this guy here, that's the data point 149, comma 85. Right, and I'm pretty confident about that because this data point here is the 150, comma 85. Right, so that's how I thought about trying to identify that one. Right, so that data point is 150, comma 85. Right, so that's the one we're focusing in on. So when I, in part G, what I was trying to do is find the, the ordered pair on my line, my graph, that had the x value of 149. Right. So in other words, if I follow this straight up to my line, then I get this data point. Right, and that point here had the ordered pair 149, comma, and then we found the y value to be about 110. Right, so 110. Right, so then what we were looking for is the residual. Right, so the residual of this would be this distance. Right, that's e. That distance is e, and since the the data points below the average, it's negative, right? So anytime you're below the line, the residual is negative. So like this dot here would have a positive residual, right? Because it's above the line, right? Same with this data point. So that's something to keep in mind, right? So that residual value, we found the difference between 110 and 85, right? So that E value, E was equal to 85 minus 110, and we found that to be negative 25, right? So that distance is the residual. And you can see it's below average because remember the red line is the average values, and we're below average because we're below it, right? Or in other words, my residual is negative. All right. So hopefully this has been helpful for you to walk through this example and kind of look at chapter 4 from like a bird's eye view and walk through a whole problem, what that might look like. Let me know if you have any questions. All right. Thanks.